I guess iLinks is meant to allow people to analyze data, links data, non-links data, and their own kind of signatures by just pointing and clicking around. And also it has APIs that allows programmatic interaction with various functionalities. So if what Amar and Vas showed LDP, and that was a question yesterday actually that somebody asked, is about data access, right? And iLinks is a kind of next step or parallel step in which you actually can analyze signatures. So I'm gonna, you navigate iLinks through one of these three pipelines. You can search, or workflows, you can search for things right here, right? For anything you can think of, and I will use Everolimus as a canonical example for analyzing signatures. And I could pick it up here, right? It found signatures, it found compounds, it found data sets that actually have Everolimus in it. But I can also go through signature workflow where I can search. First of all, I can navigate things around by pharmacological action, mechanism of action, or by known targets. Or I can just, again, put a keyword in and search through one of these links libraries or signatures. And if you go through these libraries, first four are links libraries, and they are transcriptomic signatures of gene knockdowns, of overexpressed genes, and then chemical perturbagens. Then we have P100 signatures, which are targeted proteomic signatures. And rest of them are signatures derived from various resources. Some are pre-computed by us, some are kind of picked from like, for example, EBI Expression Atlas was just downloaded from EBI. So the other way to start with a signature, right? So first you can just search for a signature. The other way is to submit it, and you can upload a file that has differentially expressed genes, right? And different level of differential expression and p-value if you want, or just without p-value, and or just paste this table right in this field. You can also submit lists of up and down regulated genes as a signature, and you can submit a gene list as a signature. And what this is gonna do, so anything you do here, you either select a signature, you find it, or you upload it. It's the next step will be to actually run connectivity analysis against the rest of the libraries. So I will search for Everolimus. There were 187 links chemical perturbagen signatures identified. I know which one I want, right? So these are kind of summaries of various things about my search that were returned. I know I want to look in MCF7 cell line, so I'm gonna filter this a little bit. And I actually know the concentration I want to use. I want to use 0.04 micromolar concentration. And now it lists a couple of signatures that fit this story. And sometimes the perturbagens are not necessarily always annotated with the name, chemical name. So the different name for this perturbagen is the same thing as Everolimus, right? So that's why two of them show up. I could query various knowledge sources to tell me more about Everolimus, but if I just click on the signature ID here, right? What is gonna happen, it's gonna select this signature and provide me various tools that I could use to analyze this signature, right? So any of these links will run a task-specific analysis on the signature. Signature itself, if I look at the signature data, what it consists of, and I can make it bigger, right, to see more of it. It consists of genes and differential expression levels, log2 differential expressions, and the p-values. So this is my signature. And the first thing that that is done when you import the signature, automatically the top differentially expressed genes are selected. In this case, by design, top 100 are selected. If I want to interact with my signature, right, and select a different set of genes, I can go here, maybe lower or increase the p-value to select signature. Now I lowered it to 0.01, and then I end up with 22 genes. So this is first way I can interact with a signature. Automatically, for any pre-computed signatures, we also have all pre-computed connections. So as soon as you select a signature, all connections are going to also be selected, and this is a very fast query, although there are billions of connections, right? They're all in the databases and can be identified right away. So if I look, for example, the example that I used in my presentation was to find something more about everolimus and its mechanism of action by looking at connected signatures, right? Connected knockdown signatures. And if I look at, there were 123 statistically significant connections, and as I can see, the genes that were knocked down in these signatures are all related to mTOR signaling. And if I now select this 123 genes signature by going here and then select all, I can run the same type of task-specific systems biology type of things, enrichment, network analysis, and so on, that I can do on differentially expressed genes. I can do now on knockdown genes that created signatures that were highly correlated to my query signature. So I can now run, for example, Enricher by just clicking on it, and if I look at the pathways, lo and behold, mTOR signaling pathway shows up as significant, right? So this is the target of everolimus, so it makes perfect sense. So this is one way to do it. I can also look at chemical perturbation signatures, and it turns out that the targets of chemical perturbagens that were highly connected or concordant with or correlated with my query signature were again targeting, were in the mTOR signaling pathway. Another thing that I can do here I will select, say, top 100 signatures and most connected to my query signature. And I will run this group analysis, right? So this is now going to grab all these 100 signatures that were connected to my everolimus signature, and I can see what is going on, right? So it's gonna put them together and provide me with some tools to analyze them together. So for example, I can look at Disney plots of these signatures by, say, time. Okay, I clicked too fast here. Well, this is thinking, right? Or say by cell line, or by core. It turns out that all of these top 100 and MCF7 cell lines. So I will look by compound. I think by compound you can start seeing some groupings, right? That compounds that of the same kind are actually grouped together, although they were all highly significantly correlated with everolimus. Or I could open our version of Morpheus, right? And it's gonna now show me these signatures again, that I can analyze them. So these are 100 signatures, and again, if I look how they're clustered by chemical, right, by the compound. And there are some other patterns that may be of interest. But if I want to know what is interesting in expression patterns of these, for example, down-regulated genes by these compounds, I can select them, then right-click here on gene symbols. And one thing that we did, we kind of overloaded this version of Morpheus so that you can, again, directly submit genes for analysis to Enricher and other tools. So that's this group analysis. There are a few other things that you can do there. I'm not gonna belabor this too much. The other things that in addition to individually connected signatures, you can look for connected perturbations, right? So in this case, what it's gonna do, it will run individual connections, right, to links, gene knockdowns, and chemical perturbagens, but then it's gonna aggregate results by looking at all signatures. So there were 24 mTOR knockdown signatures, and that kind of integrates connectivity results from all 24 signatures and gives you a summary kind of assessment of how significantly your signature was connected to mTOR signatures overall. Same thing works for the compounds, right? It kind of gives you the, so again, unsurprisingly, 42 signatures of everolimus were highly connected to your query everolimus signature. So that's about that. I'm gonna now switch quickly to the dataset workflow to just show you how you can analyze one of the more than 15,000 at this point datasets that were already pre-processed in iLinks. And there are various things that you can do. For example, you can analyze TCGA data, and maybe you can start with proteomics data for this in this case. And I'm going to look for breast cancer proteomics data in TCGA. And there is an RPPA data set, right, with 937 samples. That works with transcriptomics data just the same. To create a signature, you simply select a factor that you want to use to separate your samples into treated and non-treated in two groups of samples that you can compare. I'm going to use this classification, PEM 150 classification. I'm going to compare HER2 samples and luminal A type samples, hit create signatures. And there is actually, I guess I didn't show you this, there is a way to filter better these signatures, the samples, but it's a little involved. And again, now I created a signature, right? And there are only 266 proteins that are analyzed here, but I can again interact with these proteins, maybe select the 12 most significant ones, right? And when I look at these most significant, signature data, right? It's interesting because it gives you something that transcriptomics data doesn't give you, right? It picks up the right proteins, right? ESR1 is protein is up higher in luminal ones. ERBB2 is higher in HER2 enriched, right? That's the molecular mechanism by which these tumors arise, by expression of ERBB2. But what is interesting, if you look at EGFR, right? EGFR is differentially expressed. It's phosphorylated. One of the phosphorylated versions of EGFR is upregulated in HER2 tumors. But if you look at just EGFR, or if you look at transcriptional profile of the same samples and look for expression changes in EGFR, they're not going to be there, right? So having this proteomics angle kind of sometimes helps. So if I go back, right, I could repeat this and with another data set, but I'm gonna give you instead another view of these data sets through GRAIN. And GRAIN is, I mentioned this before, is this so I can search all GRAIN data sets. Grain is our project where we have basically an agent constantly processing RNA-seq data in Geo, and at this point we have more than 8,000, and apparently there was a huge deposition of RNA-seq data to Geo, so we have now suddenly a few more thousands to go. So all of these, so there is a separate app that actually analyzes these. So if I find data of interest from grain, right, that is processed RNA-seq from Geo, if I click here, it's going to take me to this app that runs RNA-seq specific analysis, right, using the negative binomial, right, the proper distribution to analyze data and so on. And if I analyze the data set, right, I can again go in the pretty much same way as before. It's just a slightly different interface. So I don't want people to be confused about this slightly different interface, right? But it's very similar, right? Again, you select two groups of samples that you want to compare and create differential gene expression signature. And once you run this analysis, which takes a bit, right? So this now ran HR in the background, right? The proper model and so on. And you can now just upload this stuff to iLinks, right? Go back to our old interfaces that we kind of left for grain for a moment. And then you can proceed in exactly the same way as we did before with analysis of this signature, right? Just as if it's created in iLinks. Okay, I will show one more thing there, and then I will stop because we are out of time. So for example, if you each of these outputs, you click example, right? It's gonna populate something, and this is now running a classical enrichment analysis, right? It's kind of taking these gene lists and is treating it as a gene list, right? And comparing each of the signatures of differentially expressed genes, like vectors of differentially expressed genes, for enrichment of these genes in this gene list. And so if you look at now at the results, right, so as they come in, right, some of these smaller libraries calculate faster than the bigger ones, but still they are working. Let's see which one's done. None of them are still done. I wanted to show you, yes, right. So basically, if for each concordance measure, so previously if there were little plots of scatter plots, right? But when we correlated the full signatures, but each of these connections that are made, right, when a connectivity analysis is run, produces some kind of interactive plot that allows you to visualize why these signatures are connected, right? Why was this one enriched by the genes you submit? There are various other visualizations that are peppered throughout the iLinks, but I will have to finish here because I'm already 5 minutes over the line. So I don't know, do we have any time for maybe a question or two? Is there somebody that does have?
Yeah, I think we have till 5:45 our time. They just put it in the chat.
Oh, we have until 5:45?
Yeah.
Oh, okay.
So you can go ahead.
All right, so I mean I can go through a few more examples if that's okay, or we can maybe let's wait for questions. Is there for either of us, right? I don't see the.
Hello, I have a very quick question.
Please go ahead.
Yeah. when you submit a query list of signature, I didn't see clearly. Is it possible to add the regulated direction, for example, upregulated and downregulated in this list?
Yes, so I can give you another example, right? So if we go to signatures, so there are three ways to submit a signature, right? So one of them is to upload a file like this, right? That has gene ID and then log fold changes, which gives you direction, right? And significance
Yeah.
and the p-value. But if you go here, it actually allows you to list up regulated genes, right? And down regulated
Yeah.
genes.
Yeah.
So if I hit example here, right, then it's gonna have now two different gene lists, right?
Okay, perfect.
Okay,
Thank you so much.
sure. Any other questions for either of the tools?
Yeah, we can also read from the chat if you guys have any questions. You can type them down.
Oh, okay.
Can I ask a quick question?
Mm-hmm.
So the last feature you showed was the same feature shown in the links portal 2.0. Is that right?
Yes.
That
Yeah,
is
we send the lists to Mario's portal and we get the results back.
So this is basically, just for convenience, right? If you're there already and you wanna run this search, right? Fine. It's a way of finding signatures, right? And so basically there is an API in the background that Links portal uses, and this user interface also uses exactly the same API to run the analysis. So it's gonna be, you should get exactly the same results, whichever way you use it.
But of course, in the iLinks, when you do it through the iLinks interface, you're getting other signatures as well. Because from the links portal, you're getting only the links signatures.
Right.
So if iLinks in the future includes other perturbation response signatures, like the disease-related signatures or the others.
So what's your recommendation? When should I use Links Portal 2.0 and when should I use iLinks?
So I think for accessing the data, it would be the LDP, the links portal, but for analyzing and especially integrating, as you can see in Mario's screen, you have other data sets that are not including in links, like the cancer therapeutic response signatures or pharmacogenomics, all of those. I don't know if Mario has anything to add on that, but...
Right. So if you want to do kind of analysis, I think iLinks that's exactly what I would say, right? Depending what your objective is. If you want to get data, right, then I think LDP is the right place. And if you want to analyze data, then iLinks is probably the place to go.
Thank you.
So, for example, this one is, we have these pharmacogenomics transcriptional signatures that are similar as links data, but they came from other projects. And so, for example, these are, I am not quite sure what the query was anymore, but it kind of allows you to maybe look at different things, and also has this follow-up feature, right? Especially if you use your full signature, right? That you can go through these results and run. So again, even here, if I go to say knockdown signatures, I can select, say, top hits here and run pathway analysis on these, right? And see what is, let's use something else, or a network analysis, right? That gives me, it's a follow-up thing that is not just giving you the list of connected signatures, but also allows you to expand your analysis. So anyway, that's Gene Mania, right? Enriched module that was enriched by these query genes that I submitted.
So any more questions? I think we got 3 more minutes before the break room ends.
Can I find YouTube tutorial on this anywhere by chance?
On which one? On both of them, or?
Right.
Yeah, there used to be some. If you go, okay, so let me show you a couple of things just for. So one of the things on iLinks, and I didn't mention this, is this history feature, right? So whatever you do on it is gonna be recorded on your local cookies, right? So you can go back. So I can just look at what I've done, and you can annotate your results, what exactly you did, and kind of rename them to give them informative, or reanalyze them and so on. So that's just something I forgot to mention. In the help, there are use cases, right? And we have some of the videos, but they may be a little bit obsolete because we changed quite a bit of UIs over years, so they may not be reflecting exactly the current state of UI. But if you go through these through workflows, for example, you can, if you click on any one of these, it's gonna lead you step by step, right, through some of these examples. How do you get from one point to the next? So it's not necessarily okay, so where is use cases here, right? So use cases, this is the use case, one of the use cases I did, right? And it leads you step by step, where do you click and what do you need to do in order to kind of get what I showed you right now. So again, I think we will try to have some more YouTube videos.
What you are about to see.
But so there is one on. If you go, we have actually iLinks.
Hello, my name is Mike, and I will introduce you to the Links Genomics data pool.
So there are some videos, but they're a little bit obsolete. That's what I'm saying. So I don't know what's with LDP, guys. Do you have videos?
No, we don't currently. But that's a good idea, I think, and especially now through Coursera or YouTube, you can get more information than just a flat document.
Right.
Instructions.
Yeah, that'd be great. Thank you.
Sure.
Excuse me, where I can get the recording link for this workshop?
Oh, I think they're gonna share that with everybody after the symposium is finished. So
After.
I don't think we have it at this point, but they will send the link.
Okay.
Yeah.
Thank you very much.
Sure. There is also a paper, right? At least for iLinks, and LDP also has a paper, but iLinks paper is actually very focused on some of these workflows, and there are supplements there that go step by step, are basically these workflows that I'm showing here, so you guys can, if somebody wants to take a look at that.
And the algorithms behind what they're using, the connectivities are also that paper.
That's right. That's right. So yes, if you want to know how exactly we run this connectivity analysis, there is a bioRxiv paper that describes that.
So should we conclude? Are there any other questions? I can't see on the chat anything.
Yeah, I don't see anything in the chat.
Well, thank you all for attending. I initially thought only people with camera were here, so I thought there were 3 of us, but there were quite a few people there. So I hope that was worthwhile.
All right, thank you, everyone. Thank you. Have a great weekend.
Thank you, Mario.
Thank you, guys.
Goodbye. Oh,
Thank you
Marcel.
so much.
Thank you.
Okay.
All right.
Goodbye, everyone. Bye.
Thank you.